So we started last day to talk about, we started talking about synthesis, right? And we described what that is, what is the kinematic synthesis, the design problem. And we said it has 3 stages. First, you have to define the task that you want your articulated system to do, and we worked on that last day. How to define the task as a finite set of positions, and that's the easiest case, and that's the one that we can deal with here. Second point would be to select the type, right? The type. That means number of joints, type of joints, connectivity between the joints. Number of joints, type, connectivity. And then the third part would be to do what we call the dimensional synthesis. Which is just, once you have your task, see exactly where your joints need to be located relative to the other joints in order to be able to perform that task. And this is what we will. So what we are going to do is we will select the type for right now just manually. We will say this is the type of robot we want to do. We are not going to look into how this is done automatically for right now. And then we will do the dimensional synthesis. So we will focus on this one. But before doing that, I just want to talk a little bit about why we do this and when this is important. So basically, this dimensional synthesis problem and procedure is important for systems that have a few degrees of freedom, right? So if you have an articulated system with 6 or more degrees of freedom, then you can reach any possible position, right? And I'm talking about serial, okay? Articulated serial chain with more or equal to 6 degrees of freedom. If it has more, then it's called a redundant robot, right? Can reach any position which is within its, the boundaries of its workspace. Within boundaries. Right? Why? Because our 3D space is a 6-dimensional space. It has 6 degrees of freedom. So a position has 6 degrees of freedom. If you have 6 parameters, you should be able to solve for those 6 parameters, those 6 joint variables to get that position always, right? So for these ones, we don't do synthesis because this really can reach any position. The only synthesis you want to do is make sure that at the limit your position falls within your workspace, right? So that's pretty trivial. We don't need to do that. The synthesis is important for articulated systems with less serial chains or with less than 6 degrees of freedom, or also parallel chains, right? Same thing is true for parallel chains. When we count the mobility of the chain, we find that if it's 6 or more, then we can reach any position. The difference with the parallel robot is that their workspace is smaller, so you need to define that workspace. But the same thing happens. So we could say serial or parallel is the same in this case, right? If you count the mobility. And did we ever do, it's in the notes, but I'm not sure we did in class how to compute the mobility of of an articulated chain. Did we do that? No? So you may have, especially for parallel robots, you may have a parallel robot with a lot of joints, and at the end the mobility may be 1 or 2 or 3. So just moving one of those joints, you may be able to move the whole system. And those are active joints, and the rest of them are passive joints. Okay, so you can actuate only a few of them. Let me just say mobility. Mobility, what you want to find is how many parameters you need to fully define a configuration of your linkage. Okay. Number of parameters to fully define the configuration of an articulated system. So when we talk about degrees of freedom, we don't mean all the possible joints of your system, but only those that you actuate. And when you actuate those, the system goes to a specified position. And the rest of them will take whatever value they need to take, okay?
What do we generally mean by articulated?
That means that it's composed by links and joints. So it can move, articulated. This is a general term in which we encompass anything that has relative motion between its parts. So composed of several parts with relative motion between them. Between them. Okay. So these are more general terms that you can encompass linkages, robots, anything that has movable parts. So there are formulas to compute the mobility, and that's important because that's the first thing that you can say about your system that you are trying to define is how many joint variables would define a configuration for this whole system. So Chebyshev, I want to say, I'm not sure. Chebyshev, Kutzbach, Revler formula. It's an easy to apply formula, and I think that's the one that you guys have in the notes. And it consists on counting the number of joints, counting the number of links. That would be the Kutzbach-Revler part of it is count the number of joints, count the number of links, see how much each joint, how much restriction each joint applies between two links, and you get a number. But that doesn't take into account specific geometry. So in order to solve for that, Chebyshev added something else to that formula, and it doesn't solve all the cases. We still have cases in which the formula doesn't work because it's really hard to have a general formula which is simple and gives you the real mobility. But that should be in the notes. Okay. Anyway, this is all related to the problem of the synthesis, in which we try to synthesize systems that move, right, for a given task. And those are especially important and meaningful when you have less than 6 degrees of freedom in your system. So the whole motion or the whole configuration of your system gets defined with less than 6 joint variables. And that's not so uncommon. I mean, we are used to the robot arm manipulators, and those usually have either 5 or 6 degrees of freedom or even more. But if you think about things such as fingers, usually you don't have 6 degrees of freedom in your finger, right? So those actually fall within what these robots that have what some people call reduced mobility. Okay. Many parallel robots are also reduced mobility, so they are designed, for instance, just for performing orientations or just for performing translations. You know, an easy solution to the problem would be to just make everything 6 degrees of freedom or more, right? Then you don't have to worry. But that means, you know, more complicated architecture, more complicated control. You know, you can embed part of that. If you are designing for a specific task, you can embed part of that difficulty in your mechanical structure. Okay, and that's what this does basically. All right, so assuming that we believe that we need the dimensional synthesis for something, let's see how we do that. So what we are going to do first, because it's the easiest case, is the finite position dimensional synthesis. This means the task. This talks about what kind of task is going to be a set of displacements. And there are several ways of now what we need to do is to, you know, state some equations so that we can solve for the dimensions of the system. So basically the task is this, and what we want, so this will be the input, right? Input. Okay. And then our output, what we want to get is, you know, how is this linkage, the actual, you know, location of the joints. So position of the joints at a given configuration. This is what we will get. We will get the joints are here, here and there, and with that really what we are given is the links, right? So the distance and angle between consecutive joints. Okay, configuration at a given configuration. So this is basically the dimensions of the system. And I don't want to talk about links because really you can have many different links that will give you the same motion. The real important thing is where the joints are, okay, for the kinematics. So now we need to create some kind of equations that take this as an input and then they give you this as an output, right? And this is your equations, design. This is what we call the design equations, and then we need to be able to state these equations and then we need to solve them. So we have to pass from the tasks to the system using some kind of design equations and some kind of solver. So let's talk first about the design equations that we are going to use and then we will talk about how to solve them. Both problems are challenging. Let's design equations. For dimensional synthesis. There are many ways of formulating these equations, but basically we can talk about a couple of different ways of doing it, and many people work on writing kind of vector loop equations, vector closure equations. So creating loops, you go through your chain and you arrive to this position, and this has to be equal to this input displacement that we have. So if you want, we are not going to cover this right now, we will do the second way, but if you can think of, I don't know, something, let's just take a very simple planar robot. So here we have something like this, okay? And then you want this to reach this particular point, so I have oriented it in the right way, right? So if you are given this vector, this is the point you want to reach, okay? This will be your vector P1, this is position 1. Then you can write a loop here. You can say, okay, and this is all unknowns, okay? So this vector plus this vector, let me just put them in a different color. You can say this plus this plus this plus this has to be equal to that. Okay. So let's say I don't know, S1, S2, S3, S4. We have S1 plus S2 plus S3 plus S4 equal P. Okay. So that gives you the point. It doesn't give you the orientation, but you can write similar equations just adding the angles. Okay. And if your linkage is a closed linkage or a parallel robot, then you can write a loop stating that the loop is closed within that robot. So for instance, if you have, let's take this kind of parallel robot. This is a planar 3RRR platform. Well, it may not work, but you can certainly create it. Alright? Does it work? We should calculate the mobility to see if it works. Okay?
Looks like it can work a little.
You think your intuition says yes. How about anybody else? These are all revolute joints. Let's see what you can do actually too. So for instance, you want to reach this position over here. Let me just write it. Imagine that you can move this, but let me just write the position you want to reach is right here in the center, so it's at the configuration you want to reach. So you could also write, this vector equation, right? Here, plus this, plus this, plus this fixed distance, because this, okay, equal to that, right? So it will be one loop, but at the same time, this system, this parallel robot has internal loops. And you can write also, besides this equation to reach this position, you have to say, okay, I need to reach this position, but I also have to enforce that this is a closed loop. So you have to add this other equation, right? This, plus that, plus this, which is a fixed distance, plus going down through here, coming back, you will get 0. So when you have serial chains, you just need the loop to the point. When you have parallel robots, then you have to make sure you reach the point and make sure you enforce these constraints, internal constraints. Okay? You have to write these two type of loops. The red one, which is this one, and then the green one, which is this one. Okay. This is a methodology that it can be applied systematically. If you have, for instance, the graph of your linkage, you can calculate how many loops you have in your linkage, regardless of how complicated it is, how many independent loops you have, and then you can write these equations. This is a method that works very well for planar linkages. It becomes a little bit more complicated for robots that move in 3D, okay? But this is the method. And now let's talk about the mobility, because as we were... This is a planar robot. Let's just do this little exercise so that you can practice. Planar, that means it moves on a plane. It cannot get out of the plane, okay? Parallel, has 3 legs. So we write this 3, and then you state the topology of each leg. R, R, R. 3, R, R, R robot. That means it has 3 legs, and each of them has 3 revolute joints. Okay, so let's we can apply here the Kutzbach, Revler, and we can add the Chebyshev part of it. We are going to implicitly state it because we know already that it works on a plane. At the Chebyshev part of it, where it computes what is the space in which the system is moving. So in this case, it's the plane. We can see it. We don't need to compute it. So then you count the mobility like this. You say the mobility or the degrees of freedom will be 3 times the number of links minus 1 plus the sum from I equal 1 to the number of joints j of 3 minus the degree of freedom of each joint. Then you have this formula in the notes, but let me just write what everything else. And number of links counting ground, counting the ground, which means the attachment. Okay, the base is also counted, and then we take it out because it doesn't move. But j number of joints, and fi, this is the degrees of freedom of that particular joint. Okay, degrees of freedom of joint I. So for instance, if it's a revolute joint, it only allows rotation about that axis, so that it means degrees of freedom equal 1. So if we count for, let me just put this here, if we count for this case, and let's count the number of links. The ground is 1, then this leg has this link here, 2, this link here, 3, 4, 5, 6, 7, ground is all the same, and then 8 is the platform. This is what we call the platform. So in this case I would say n equal 8 different links, and the links are the parts that will have relative motion. And now let's count the joints, and they are all revolute. 1, 2, 3, 4, 5, 6, 7, 8, 9. J equal 9 are joints. And if they are revolute joints, means that fi, the degrees of freedom, is equal to 1 for each of them. The revolute joints allow only 1 degree of freedom, right? So let's see what we get. See if this one is going to move or not. 3, 8 minus 1, minus 9, 3 minus 1. And that is the 21 minus 18, 3. So it does move, okay? It not only it does move, but it has 3 degrees of freedom, which means it can actually reach, any planar position within its workspace, and that's determined when you fully extend. You will see when you fully extend one leg, that's as far as it can go in that direction, right? So this is easy to calculate, but remember, you need to know in which space you are moving. If you try to use the general formula for this one, it won't work, because this has a very specific geometry in which all the joints are parallel. If the joints were arbitrarily oriented, it won't move, okay? It wouldn't move. And let me just show you that. Notice that for arbitrarily oriented joints. And now let's assume that there is no subspace of motion, so it can move in general in 3D, in which case we can just use the general formula, which is 6n minus 1 minus the sum of j equal 1 up to I equal 1 up to j, I equal 1 to j of 6 minus fi, okay? So now if we put out, the numbers haven't changed, so we have still 8 links, 9 joints with mobility equal 1, 6, 8 links, right? 8 minus 1 minus 9, 6 minus 1. What is that? 42 minus 45 minus 3. So instead of having all the joints parallel, which allow the planar motion, you had the links, the joints arbitrarily oriented, then this will try to go in this direction, but this tries to go in this other direction, and it's jammed, it doesn't move, okay? So that's why looking at the subspace of motion of your particular linkage allows you to solve some extra cases. Anyway, we were talking about the loop closure equations, and I was saying if it's a serial chain, then you just have to make sure that you can reach that point along your chain. If it's a parallel robot, then not only you have to state that you reach that point, but you have to state that there are other constraints within your system. Okay, these points cannot move freely because they are constrained by these other ones, okay? And then you have to state that, making different loops. This is the method we are not going to use for right now. The one that we are going to use is the other one, which is equating or using the forward kinematics equations, and that's why we spent some time working on that, using the forward kinematics equations. The loop method and the kinematics equations method are very related. I mean, they are not really independent, but they are stated differently. In this case, what we do is we consider that the desired position, right, this is the position we want to reach, and we have the transformation from here to there, okay? So this will be P. We can write it as a 4x4 homogeneous matrix. We can write it as a dual quaternion, okay? Let me just say this is P. This is not a vector, so let me just put the hat. This is the displacement. And what we are going to do in order to create equations, we are going to do similar to what we do with the inverse kinematics problem. We are going to equate the transformation along the articulated system, along the robot, to this displacement, right? So if we use the absolute forward kinematics, we will just let's say for a n-jointed serial robot for an n-jointed serial robot, we will have, and we are talking about the absolute transformation, so let's just write it as we know how to write it. That will be S1 of, I'm putting theta as the variable, it could be a slide 2, okay, S1 theta 1, S2 theta 2, Sn theta n, and now if we want the absolute forward kinematics, we multiply times the first transformation, right? Times, let's call it S0. So this takes us from the fixed frame to the end effector, whatever that is, right? To the end effector frame, and that's defined by this S0, okay? So this will be our forward kinematics. Let's just call it D. D equal to that. And now we want this to, for certain angles here and for certain dimensions, to be equal to the position we went. So you just equate those to the desired position, P. So we want for certain values of the angles of theta, theta 1 to theta n, and of the joint axes. That means where the joint axes are located, and those are the Plucker coordinates of the axis, S1, Sn. This serial chain has to be able to perform that displacement. The serial chain must perform displacement P, okay? So this is exactly what we do for the inverse kinematics. Remember, we take the forward kinematics of our robot, we equate to a given position we want to reach, and we solve for the angles. You can think of this as a generalized inverse kinematics in which you have to solve not only for the angles, but also for the location of the joints. Everything is unknown. So it's a little bit more complicated. I mean, inverse kinematics sometimes is complicated already. The synthesis is, of course, much more complicated. You have a lot of variables, and you get very, very nonlinear problems. Let me just write that. Think of it as a, I'm going to put generalized inverse kinematics in quotes, because the name generalized inverse kinematics is used in inverse kinematics with a different meaning. Okay. Inverse kinematics. Where you need to calculate not only the joint angles, the theta I, but also the the location of the joint axis. Joint axis SI, and that means the Fluker coordinates, right?
And earlier in the inverse kinematics, we used to find out the joint angles only. And in this one, the additional thing is the Fluker coordinates.
Yeah. So when we did the inverse kinematics, you knew what robot you were using already. You had the Fluker coordinates of your axis. You know, this axis is here, and this one is at 90 degrees, and this one. So that's already given, and then you just have as unknowns your thetas. But in this case, we don't know the axis. That's what we want to find out in order to design the robot. Okay, will this axis be at 90 degrees of this, or at 45, or maybe they will be parallel? And that's what the system is going to give you. So you need to solve for the actual, geometric arrangement of your robot. Okay, how are your joints going to be located with respect to the other joints? Okay. And this problem that seems not so complicated is still very, very much unsolved. Okay? Still a lot of research to do in this, just because it becomes very complicated very easily. So let me tell you how unsolved it is. Okay. So this robot, just a revolute joint. Okay, that's easy, right? Where to locate this revolute joint to reach a set of positions? That is done. Okay, that one is easy. We can do that. Now let's take two revolute joints. A robot that is just a couple of revolute joints. And now, what we want to know is, you are given your task, and you need to locate this first joint, then look at the angle and the distance between these two joints. Okay, this one is easy. This one is done. I'll show you then later what you get. In this one, actually, these are very nonlinear systems, so in this one you get two different solutions, two different robots that can reach up to a certain number of positions. Two solutions. And the maximum number of positions you can define is 3 positions. We will do that counting next. Then we go to a robot which is just 3 revolute joints. Okay, I will be the next one. 1, 2, 3. Still an easy robot, right? I mean, most of the industrial robots have more than 3 degrees of freedom, more than 3 joints. So this is not solved yet. And from here on, nothing else, okay? And when I say not solved, what I mean is we can state the equations, but we cannot solve them in any other way but numerically. We don't know how many solutions are there. For this we know there are 2 solutions, in fact there are 6, 4 of them are complex, 2 are real. This one, we cannot even reach a position with this, but in this one we know more or less how many. It's not even solved, this one. The equations become so big that we don't have an algebraic solution. And in fact, that's one of the things that Ali is working right now. We are trying to apply Grosvenor bases to solve this problem. Okay, it's kind of simple. If you put 4 joints, you get thousands of solutions. If you put 5 joints, who knows? Okay, so the systems become very big. Of course, if you have prismatic joints, those are a little bit easier to solve for. Okay, so the revolute joint is kind of the more complicated one. But anyway, the equations become very nonlinear, and we will see that very soon. Now, a related problem to this is, okay, we talk about the task, and there is something we can calculate, is how many arbitrary task positions can we define we define for exact synthesis. For instance, when we have the robot that I just put first, right? Just a revolute joint. Yes. You know, if we define 10 positions, just arbitrarily oriented in space, is just a revolute joint going to be able to hit those exactly? Well, the answer is not, right? How many can we hit exactly with this? You know, we can always hit one, right? Because imagine this is my first position. I want this robot to pass through this position. Okay. So the one is easy because you make the end effector, you know, from here on. You just make this link going there, right? With the orientation that you need to be. And there is the one. So one is always easy. You can always reach one position by just locating your robot there. How about the second one? Once you have this, can I reach this other arbitrarily specified position? Well, you can only rotate about this. So if this position is not on this curve that you rotate, you cannot reach it. So you cannot even define two positions for one single joint, okay? Cannot reach two. In order for the robot to be able to reach two, it needs to be a cylindrical joint. You need to be able to slide and translate, right? At least. Of course, this is a simple case that we don't even solve, but there is a way to calculate. We have a formula for that. To calculate how many positions we can reach, and the formula is just equate the number of equations that we can create to the number of unknowns we have, right? Number of equations equal number of unknowns. Okay, and now we are going to test our knowledge here. So we are talking about the forward kinematics method, and we are going to use dual quaternions. So imagine this robot. So n jointed serial robot. We can write the forward kinematics for that. And let's talk about, we are going to use the relative, okay? Relative displacement. So relative displacements, which means that we will have so if we are given a set of n positions, we will have n minus 1 relative displacement, right? For m positions, m minus 1 relative displacements. What we do is we take one as the reference and we subtract that from the other ones, right? Or we do the inverse times that, right? For instance, if you have, let me just, p1 to pm, and we take that as the reference, and we can take any of them. If we do the relative, we will have p21, p2, pm1, m1, which is equal to pm, sorry, p1, sorry, let me just start over, p12, p1m, p12, p1m, which is equal to pm, p1 inverse. So we have m minus 1 when we talk about relative. So how many, let's state the forward kinematics equations for this n serial robot, and we have to do it in general. Everything is unknown. So it will be, you know, S1 of theta 1, Sn of theta n equal to P1 I Okay, so I'm going to put theta 1i, theta ni, meaning the angle to reach that position. Relative displacement P12, P13, P1m. So from the first position, for instance, to any other. I equal to m, right? So these are the design equations we can create. And this should have had there. We can create m-1 sets, right? Now each of these is this is a forward kinematic, which means this is a displacement, and if it's a dual quaternion, it has 8 components, right? Dual quaternion, 8 components, 8. But we know that for it to be a unit dual quaternion, which means it's a displacement, we have 2 constraints in there. It has to be unit, and the first times the second has to be equal to 0. Then 6 independent components, and those are the ones that count. So these are the equations we can create. We can create 6 times m-1 independent equations. 6 m-1 independent equations. Is this clear? So 6 for each quaternion, and we have m-1 equalities in which we equate to the desired position there. All right. Now we have to count the number of unknowns. Unknowns or parameters we need to solve for. We have S1, S2, Sn, right? S1, Sn. Remember, these don't change from equation to equation because these are always at the reference configuration. We move always from the reference configuration to the next, and the axes are expressed in the reference configuration, right? Expressed in reference configuration. So these are Plucker coordinates of the lines. And how many components does a Plucker coordinate? How many Plucker coordinates we have in a line? We have 6, right? But if it's a line, then it has to be unit, the direction, and the moment times the direction has to be 0. So there are actually 4 independent. For each line, okay? Yes. Where are we?
Unknowns.
Unknowns, yeah.
S1 to Sn.
S1 to Sn, the joint axes.
And expressed
In reference configuration. Yeah. Expressed in the reference configuration, whatever one you take as your reference. Each of them will have 4 independent Plucker coordinates, 6 in total plus 2 constraints. And we also have the angles bothering around, right? So we have the theta 1i, theta ni, I equal to m. So it's a total of n times m-1. If we are talking about a serial chain in which each joint is independent, and we are talking about 1 degree of freedom joints, okay? For 1 degree of freedom joints. And this one we have 4 times the number of joints for n. Okay. So I'm going to put here revolute because the prismatic joints are even easier than that, okay? So we just now equate this and see how many positions we can get as the maximum. So you have 6, let me just say that, equate. Six m-1 equations has to be equal to the number of unknowns for n from the axis plus n times m-1. Number of equations, number of unknowns, and now we solve for m. Okay. So m6 minus n times m equal to 4n minus n, so 3n plus 6, right? Six minus n. Is that right? I think so, right? This is the maximum number of positions we can define. For a serial robot with revolute joints, okay? There are other particular cases later, but this is the basic. So for n equal 1, which means this is our robot with one single revolute joint, for n equal 1, m will be equal to 3 plus 6 divided by 6 minus 1, 9 divided by 5, and that is 1 plus 4 over 5, right? Which is less than 2 positions, and that coincides with what we saw. No, you can define one position, but you cannot define a second position. A single revolute joint won't be able to solve this. N equal 2, this is the RR serial robot. M equals 6 plus 6, 12 divided by 4, and this is 3. That means a serial robot with 2 arbitrarily located revolute joints can pass exactly through up to 3 positions, no more. If you define a 4th one, you can make it go close if you want, but it cannot fully reach that position if it's an arbitrary position. Okay. Let's keep counting. I don't want to extend. Let me just move to another page. 3n plus 6, 6 minus n. 3n plus 6, 6 minus m. 4 n equals 3, so this is the RRR robot that we will be working on. M will be equal to 9 plus 6, 15 divided by 3, and this is 5. So for the 3 arbitrarily located joints, a robot with 3 arbitrarily located joints, revolute joints, you can define up to 5 positions in space. That's what the maximum it can get. And then n equal 4 is what? M equal 9? And n equal 5? 21. Okay, so here it starts becoming interesting. You can define 21 positions however you want, and a robot with 5 revolute joints will be able to reach those. It's already a well-defined task, 21 positions. See what happens when we go to a robot with 6 degrees of freedom. 6 minus 6 equals 0. You can reach infinity. which is consistent with what we know, which means if it has 6 degrees of freedom, it can reach any position. And from there on, the formula stops making sense, but obviously you can reach all the positions. So when we, the 4 and 5 degree of freedom serial robots are fairly common in industry. Not so much the 2 and the 3, but the 4 and 5, 4 mainly for working on subspaces like in planar, scalar robots and similar. 5 are pretty general robots, and it's good to realize that you cannot just buy your robot and expect it to perform anything, because it won't be able to perform anything. Okay, it's limited. Okay. All right. So now that we know how many positions we can define, we could write the equations. But before doing that, let me tell you that there are other cases, because we not only have revolute joints, we have other joints, right? So let's put in there the prismatic joint. If we add P joints, prismatic joints have a particularity, and that is ugly, but we have to take it into account. When you have a translation, it turns out that it doesn't matter where your direction of translation is located. You will perform the same exact motion. Okay? So if you have your translation vector here, you will move in this direction. If you have it here, you will move in the same direction. So for translations, only the direction matters. Yes. For translations, only the direction matters, which means if this is these are the Plucker coordinates of a prismatic joint. No? Okay, here's your prismatic joint. This will disappear from your equations the moment, completely. You will only see S. Only S in design equations. Which means that for prismatic joints, when we do that counting, we have to consider only 2 parameters, because it's a unit vector. So we need to make our formula more general. Okay? The counting formula generalizes to, now we have a robot with n joints, right? N jointed robot. Now we have R revolute joints, P prismatic joints, okay? R revolute joints, P prismatic joints, and of course R plus P has to be equal to N. They are still 1 degree of freedom joints, and we are still talking about serial robots. So when we do our counting, the number of equations is the same, 6m minus 1 for m positions. But now we have to equate that to revolute joints, 4 parameters for the whole Plucker coordinate. So 4r. Prismatic joints, 2 parameters only the direction. 2 independent, 2p. And now, it's either n or r plus p for the number of joint variables, right? R plus p times m minus 1 joint variables. Whether they are slides or they are rotations, it's one variable for each. And now we have to solve for m here, and I don't remember, so you guys will have to help me. So we have 6m minus r plus p, so m equal to something that has 6 minus r plus p here, right? And here we have 4r plus 2p minus 1, so 3r plus p plus 6, right? I think that's the formula. And now let me add something else. If your joints are not general, if there is a constraint between them, for instance, I want two of my revolute joints to be parallel, you can add that constraint as one more equation, okay? And I'm going to put that here. C. Equations constraining geometry. That can always be added. This is the most general case. If you add C, then it's a little bit less general. So you have to put a minus C here for the number of constraints. Scalar constraints, each of them. Let me do a couple of examples and then using this formula. So now imagine that you want a robot that we can say is 3R 1P, for instance, right? 3R 1P. That means 3 revolute joint, 1 prismatic joint. So this is something like this. Let me just do 1 revolute, 2 revolutes, 3 revolute joints, and then here we have 1 prismatic joint. And here is our end effector, okay? So this is the axis of our prismatic joint, 3R1P. And if we calculate that, okay, so 3 times 3, 9, 10, 16, no constraints, so 16 divided by 2, right? Which is 8. So this robot can reach up to 8 arbitrary positions, okay? And so on. I'm not sure this is in the notes yet. I don't think I have posted the synthesis chapter, so I'll do that, and you will see that there are more things you can do in these formulas. But it basically at the end is always the same. It's counting number of equations, counting number of unknowns, and that gives you the maximum you can define. What happens if you define more positions than that? Then you do an optimization. You go as close as possible to those positions. And that's the case in general when we define for a curve or for a workspace, right? What happens if you define less than this? For instance, less than 8 positions for this robot? That means you have infinite solutions. You can select something arbitrarily. For instance, okay, I define 4 positions or 5 positions, and I'll fix the first axis to be vertical and be located here, for instance, right? So this, when we solve for the exact number of positions, we don't have any freedom as a designers to specify anything. Everything is given by the calculation. All right, next day I think we will just do some examples.
So how we are defining the scalar term here?
See?
If there is a constant?
Yeah, for instance, you could say a possible constraint would be, imagine that this and this need to be parallel or perpendicular. So you would do S1 dot S2 equals 0, for instance. Or if you want, let me just say, if you just want the directions to be perpendicular, S1 dot S2 equals 0. This is a scalar equation. And these are all unknown, so S1x, S2x plus S1y, S2y equals 0.
It counts as a one constraint. Yes.
Say that again?
S1 dot S2 equals 0, and these two C is equal 1, yes?
That's a constraint. So in this case, if you impose this, then C equal 1, exactly.
C is the number of constraints.
The number of constraints, yes. The number of equations, okay, maybe I should put that, number of equations constraining the geometry.
So whatever constraints there may be, So it doesn't matter. We just put the.
You add, it will be, yeah, exactly. It may matter. I mean, if you define constraints that are all, and we can talk more about it, or apply to the directions, for instance, you may constrain more the orientations than the translations. That may happen. Okay, that's need to work more into. What happens is what we saw, that the displacements is really two subspaces. It's the rotations and the translations, and it's a product. It's a semi-direct product of these two. So sometimes you may over-define one and under-define the other. That may happen, and there are formulas to take that into account. For right now, let's just consider that any constraint you put on the geometry, you can add the number of constraints there. Okay. All right. So next day we will do some simple examples, so that for you to see how complicated the equations become.